If 5 people come from math help and there are 12 desks, how many ways can the students be seated? And yes, it's going to be a big number. This is an interesting question because I find it's a spaces question. However, there's a common mistake that gets made. And the common mistake is a person draws 12 spaces because you're used to having students sit in desks, so it makes sense to make spaces as desks. However, we have to remember that our spaces are our decisions. And in this situation, only 5 decisions need to happen. Person 1 comes in and they have to decide where they're going to sit. Then person 2, then person 3, then person 4, and then person 5. Okay? So the first person that comes in, there's 12 desks available. How many choices do they have? 12. Okay? Now we're going to make an assumption here, because I don't know if you've ever been in math help, if you're sitting at a desk and another student comes in, if they sit on your lap, it's like awkward, right? So we're going to assume that person number 2 is not going to sit on the lap of person number 1, leaving only 11 desks or choices left. And then 10, and then 9, and then 8. This is the same as 12 P5. And you can multiply it out. How many seating plans could we have in this classroom? There are 32 desks, and there are 27 of you if everybody showed up. Because it makes sense that you could do 32 P27. This is where the formula is kind of nice, because it would be there would be 27 decisions to make. Person 1 would come in and could sit anywhere in the 32 desks. They'd have 32 choices, then 31. If we wrote that out, it'd be really annoying. 32, 31, 30, blah, 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 all the way down. I don't even know if my calculator is going to like me if I type this in, but I'm going to go 32P, and the P button on your calculator, I'll show you on here. I hit the wrong. Under the math button, you can go over to probability, and you have the factorial and the NPR. So I do 32P27. Wow! Do you know what this E33 means? That's scientific notation. It's like, I can't write out all the numbers, so I'm going to stop here and say this is times 10 to the 33. In other words, if we wrote out this number, I wanted to see it. Maybe I can see it on my... Equals 219275697 that was ugly 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. That's what that e to the 33 is. Okay? So I once said to my class, put a new seating plan on my computer. If you can guess the right seating plan, I even took out the empty desks to make it a little bit better. But if you could guess the right seating plan, you got 100% in the course. You wouldn't have to come for the rest of the semester. Just exempt you from the final exam and everything. Just get 100%. Right? But this is your chances of getting it right. So not very good. Although I was a little bit mean. So I got the first person to guess, and they guessed and they got them wrong. They got the first one wrong, so I said, your turn's already over. And eventually someone guessed the first person right, and like, okay, so that makes it easier for Declan because it's later on. You know who at least the first person was. But what was mean is part of the way through, say it was Emily's turn, I was like, okay, guess. And I was like, just pretended she got all of them right, all along. And then I was like, I'm lying. She got like the second one wrong right away, but it's almost impossible to get that right with that many choices. I'm going to change this to match our textbook. I like our textbook's wording better. These are our Mississippi questions. We've done these before, so some of these we can do quickly. Egg. If you're like, I'm going to make my new password for my bank, I'm going to rearrange the letters of the word egg. Okay, not very good, but you only have 3 letters to begin with. If they were all different, it would be 3 factorial, but you have the 2 identical G's, so we have to divide by 2 factorial. You would have only 3 passwords. Not very strong. Mississippi is a skiing place in Manitoba. 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. 9 factorial divided by, we have 3 S's, 3 factorial, 2 P's, 2 factorial, 2 I's, 2 factorial. And you can type that into your calculator and get an answer. So we have to recognize different situations that would have identical objects. Okay? Here we have a street, and on the street there are type A, type B, and type C. Have you ever seen this in an area where all the houses look the same? It's because when they decided to build them, they sort of like, this is the plan for this house, and we like have 2 or 3 different, and I mean they change the outside so they look a little bit different, but a lot of the houses look the same. So if this was the question, this is like a Mississippi question because we have identical objects. And instead of the word Mississippi, this time we've got And if you add these up, we have 9 letters. We have to divide by 3 factorial for the A's, 4 factorial for the B's, and 2 factorial for the C's. So we've done questions like this. What? And we saw these questions before already. We can draw a grid. And John lives 3 blocks north and 6 east of school. So the school is here, and John lives there. So if he is walking home from school, he would have to go north 3 times and east 6 times. So this becomes an identical objects question because you can have 9 factorial over 6 factorial, 3 factorial. And if I put this into my calculator, I get 84 ways in total. And you remember when we did this in class, we counted pathways. So if we started here at school, does it make sense that each of these green dots, to get to any one of those green dots, there's only one path. Because it's a straight way to get to this straight. There's only one path to each of these. But then, if I wanted to get to this dot, there would be 2 options because I could go through this way or this way. This one, 2 plus 1 would be 3. Here, 2 plus 1, 3. 3 plus 1, 4. 3 plus 3, 6. 3 plus 1, 4. 10, 10, 5, 6, 7, 15, 20, 35, 21, 28, 56, 28, and 56. Look at that, 84. It works out to be the same number. Okay? So now we're going to add something interesting to this question. So there's 84 ways that John can walk home. We are going to now say that John is walking home and Susie lives here. And now every time that John walks home from school, he always has to walk by Susie's house. So what does that mean? That means he will no longer, we'll take out a, I'll do it that way. It makes sense that he would no longer go to these parts, and he would no longer go to these parts because he's walking by Susie's place. So in this one, it might make sense to say, okay, these are still, I'll do them in green. All of these points here would still all be 1, 1, 1, 1, 1, and 1 plus 1, 2, 1 plus 2, 3, 1 plus 3, 4. There would be 5 ways that he could get to Susie's house. And then this dot would be 5 plus 0. Does it make sense? This dot would still be 5. And this one, to get here, is only this path, so that's still 5. And this path would still be 5, and this path would still be 5. And 5 plus 5 is 10. 10 plus 5, 15. 15. And there would be 30 ways that John could get home if he had to walk by Susie. Okay? Something happens, and John has to walk home, but he is not allowed. It's like, maybe, it's like a stalker kind of question. He's now no longer allowed to walk by Susie's house. He has to avoid that. How many ways could he get home now? And this is where we could use that not strategy. If there are 84 ways in total that he can walk home, and we figured out 30 of them walk by Susie's house, does it make sense that there would be 54, 84 minus 30, 54 left where he doesn't walk by Susie's house? So those are some of the not strategy and things that can come up. We can start off with a simple question and add one little twist to it, and now it becomes a little bit more complicated. Another new strategy. This strategy I call the grouping strategy. Sometimes you want to count things, but you want certain things to stay together. Okay? So what would be, maybe you have like a stuffed animal collection, and you have a shelf at home with your stuffed animals. And you have like, how would you want to organize them? You have like your real animals, and then you have like your fake animals like dragons and unicorns. And then maybe Beanie Babies have their own little section because those ones are special to you. So you first decide to group things into certain things, and then in those groups you need to like rearrange them in a bunch of different ways. Okay? I don't have a stuffed animal collection, so I went with a math book collection. I know all of you probably have this hidden at home as well. So, I want to arrange my 4 calculus books, 5 algebra books, and 4 geometry books on a shelf. And I want to keep each of those groups together. And this will be, sometimes on the test, I'll make sure that I put like they're different, or you can ask, are these books different, or are these books identical? Because grouping questions sometimes get confused with identical object questions. Are the objects identical, or are they different? So I have 4 different calculus books, 5 different algebra books, and 4 different geometry books. Now the strategy that was listed on the last slide is, first, figure out how many groups you have, and do that factorial. So that's your first decision, and you can, underneath that decision, write groups. And the number of choices you would have would be 3 factorial, because there's 3 groups. 3, 2, 1 would be 3 factorial. Now I decided maybe I put my algebra books first, then I put my geometry books, and finally my calculus books. It doesn't matter the way that I order, but this could be one of the options. If I put my algebra books first, how many choices do I have for that? Well, there's 5 of them. How many ways can you arrange 5 objects? 5, 4, 3, 2, 1. 5 factorial. How many ways could I arrange my geometry books? 4 factorial. How many ways could I arrange my calculus books? 4 factorial. And you see how we made spaces? We're sort of using our spaces strategy. We had decisions to make, and then we had lots of choices in each of those decisions. So we would multiply all of these together to get a big answer. So a grouping strategy, if you want things together in a group, first count how many groups you have, then think about each group separately and see how many ways you could arrange things in those groups. And here's our first grouping question. 5 people, Amy, Bill, Jill, Lee, and Tom, are at the park bench. And then all of a sudden, Jill and Bill want to sit together. So how is this a grouping question? Well, you've got Jill and Bill, they're a group. They have to be together. You still have Amy, Lee, and Tom. And so for the first thing, if we recognize this as a group question, how many groups do we have? And this too is where things get a little bit tricky in group questions. Some people think there are 2 groups, but there's actually 4 groups. Because do Amy, Lee, and Tom have to sit together? No, they could be broken up. They're like individual groups. So number of groups, we would go 4 factorial. Okay? Sometimes people think of this as like Jill and Bill. Have you ever had like a couple at school where you never see them apart? It's like you start to refer to them by one name. They're like one person, one entity now. The Jill Bill, right? There goes the Jill Bill. I know that when I was in school, there was Derek and Carrie, and they never were apart. We just called them Carrick. We combined their names and just called them Carrick, because you would never see them apart. And it was like whoever got to school first would stand by the door and do nothing until their second half of that person arrived, and then they would all date together. So some people think of this not as 4 groups, but they think of this as 4 people. There's still Amy, Lee, Tom, and the Jill Bill. And how many ways could you arrange 4 people? 4 factorial ways. Then you look at each group individually. There is the Jill Bill group, right? On Mondays, Wednesdays, and Thursdays, they hold right hand, left hand. On Tuesdays and Thursdays, they hold left hand, right hand. So we've got 2 factorial ways of arranging the Jill Bill group. But everybody else, you could put Amy, Lee, and Tom as 1 factorial, 1 factorial, 1 factorial, or you could just omit that. Can you see that that's not necessary to write down? But the grouping strategy says, how many groups do you have? Then rearrange each of your groups. But the 1 factorial is redundant. So it would be enough just to show 4 factorial times 2 factorial and get 48 ways. It's going to be interesting because we have an Amy in class, and so it'll add to the story. Something happened, and now Lee and Amy also want to sit together. And I know what you're thinking. Poor Tom. Don't worry. Tom gets his revenge in part C. We'll get there. All right, so now We've got Jill and Bill wanting to sit together. We've got Lee and Amy wanting to sit together. Oh, poor Tom. How many groups do we have now? We have 3 groups, so that would be 3 factorial. The Jill Bill and the Laney. And you could put Tom there, but you wouldn't need to. Poor Tom. And we would get 6 times 2, 12 times 2, 24 ways. Part C. Something happens. There we can. I'm going to just erase this. We don't need to see all of that right now. But something happens, and Jill and Bill must not sit together. You think it's still funny that they would still come to this park bench? It's like 5 people on a park bench. It's like if something terrible or awkward happened, they probably wouldn't come to the park bench anymore. But whatever. Jill and Bill must not just sit together. For this part, we're like Lee and Amy, they can sit together, they don't have to, it's kind of all good that way. But we want to make sure that Jill and Bill must not sit together. And sometimes when we have the word not in a question, it's a hint that maybe the not strategy would work the best. So a little review of the not strategy. That's where we count all of the ways and we subtract the bad ones. Well, all of the ways would be just anybody sitting on the park bench. Does it make sense that the all would be 5 people on a bench, 5 factorial? Then the bad ways, well, the bad ways is when Jill and Bill are together. Can you see that we counted that in part A? We found out there was 48 ways that Jill and Bill were together. So if we take all 120 and minus the 48 that are bad, would leave you with 72 ways that they could go to the park bench, not sit together. And this is the easiest way of counting that. So this is an example where the not strategy is the best way to figure it out. Too bad we didn't have someone named Lee in this class. Even interesting. And our last strategy with permutations is called cases. So we learned grouping strategy new today. We're also going to learn cases strategy new today. The cases strategy is when you cannot count something all at once. You have to do it in little sections, in little cases. Count one little case first, figure that out, then count something else second, figure that out, maybe something else third, and once you've counted all the different situations separately, we're going to add them together to figure it out. Okay? You will see cases when you get things like at most 3 different digits. So it could be case 1, as this is what we'll do. We'll write out a case and say what we're counting. 3 digits. If I had 3 digits, how many numbers of at most 3 different digits, so we're not allowed to repeat, can be formed using the digits 0 to 9, okay? There is a restriction on my 3-digit number that your first number is not 0, because then it's no longer a 3-digit number. So I would have 9 choices for that. How many choices do I have for my second number? 9 again. One of them is used up, but 0 gets added back in, and then there would be 8 choices left for, what would that be, 648. And because it said at most 3 different digits, we have a case 2 where we count our 2-digit numbers. And we would have 2 spaces. And again, there would be a restriction. Nine choices for the first one. And then 0 could get added back in. 9 choices for the second one. And then case 3, 1 digit, How many choices for your one digit? 10. Is 0 a digit? Is 0 a number? Okay, 10. And then you would add them all up, giving you 739 different numbers. If you think about the strategy you would have had before this unit, before spaces, your strategy probably was listing all the numbers and then counting them up. This would take a long time to count. And we just counted all the ones, basically from 1 to 1,000, we just counted all, it was 0 to 1,000, that don't repeat. There's 739 numbers from 0 to 1,000 where the numbers are different. The rest of the numbers, that would be another good question. How many numbers from 1 to 1,000 or 0 to 1,000 have numbers that repeat? Then you would use the NOT strategy. You take all 1,000 numbers, subtract these 739, and you'd be left with all the numbers that have a repetition. Just still quicker than counting, okay, 11, 22, 33. Oh, but then there'd be 101, 202, 303, 100. Too many. Our cases question, a very typical one, and I always put one like this, something like this on the test. It's very typical to have a cases question when you have a restrictions question with two restrictions. So we learned about restrictions the other day that said if you have a restriction, deal with that first. In this question, it says how many three-digit numbers can be formed with 1, 2, 3, 4, and 5, no repetition, and they have to be greater than 300 and even. So if I tried to do this just with spaces once, I'll change to red to make a mistake, okay? There is a restriction on our first one. If it's greater than 300, does it make sense that our choices are 3, 4, and 5? That would make the number greater than 300. It also has to be even. So there's a restriction on my last digit. If it's even, does it make sense it's going to have to end with a 2 or a 4? The restriction strategy says do your restrictions first. But I have two of them. Which one should I do first? Oh, maybe I choose this one. How many choices do I have? 3. Where do I run into a problem? How many choices do I have here? 2? But what happens if I pick the 4? If I pick the 4, then I only have one choice. If I didn't pick the 4, then I would have 2 choices. So I have a problem here, and the problem is because we have a restriction that overlaps. So what we do is we break up our restrictions into 2 different cases, or 3 different cases. So it could look like this. I often, I'm going to switch out of red. I'm not going to make mistakes anymore. Case 1. I often take the restriction that has less things. So my restriction at the end for the even only had 2 choices, the 2 or the 4. So I make my case 1. I'm going to end with a 2. I'm telling you, that's what I'm doing. I'm counting all the numbers that end with a 2. Does it make sense that you have only one choice there? That would leave us with, what am I left for my first restriction? Can you see that all 3, 4, 5 are possible? I have 3 choices there. Then, no restrictions on the middle number, but how many numbers do you have left? We used up the 2 for sure, and then we either used the 3, the 4, or the 5. We don't know which one, but one of them is gone. Does it make sense that you have only 3 numbers left? Because maybe, and I don't know for sure, but let's say I chose the 4. Then for my middle number, all that's left, it could be a 1, 3, or a 5. Multiply this together, gives me 9 ways. But that's counting only case 1, only the numbers that end with 2. So then I go and I say, well, what haven't I counted yet? Case 2, I'm going to end with a 4. 3 decisions. Now my last number is a 4. Still only one choice there. My first restriction, can you see that now you only have 2 choices for that first number? Because it has to be bigger than 300, but the 4 has already been used. So now there's only 2 choices there. You've used up 2 numbers, leaving 3 numbers left. Add up your cases. And this is our first example of something that actually took a while, and our number is small. So we only got 15. Right? Sometimes we do something and count to a huge number very quickly, and sometimes we count and just get a small number not so quickly. Yeah.
Why is it 3 instead of 4?
3 instead of 4 in the middle?
Yes, with that, the second one.
The second one?
Yes.
Well, in the second one, so if I'll rewrite. I have the numbers 1, 2, 3, 4, and 5. And I'm not allowed to repeat. I decided I'd make my last number a 4. Now, my first number is either a 3 or a 5. I choose one of them. 2 choices,
Oh, okay.
but I only choose one of them. If I chose the 3, how many do I have left? I still have 3 choices. If I chose the 5,
Okay.
I still have 3 choices left. So we have to be careful because sometimes our brain makes us think, why did you put a 3 there? I didn't put a 3 there. I had 3 choices. The number that goes in the decision space is how many choices you have. Underneath each decision, I like to write out my choices because then it like reminds me, oh yeah, I can't write 4 here because I used it up already here. Okay? You could do this same question with 3 cases. You could say, start with a 3, count it. Start with a 4, count it. Start with a 5, count it. And it would work out to the same number. So you can choose either of your restrictions and count that up. And another typical cases question looks like this. This time, we just want our number greater than 232. Doesn't have to be even, just greater than 232. Why can't we do this right away? So first of all, we'll go through why cases are needed. Okay? If you tried to count this directly, what are the possibilities for the first number? Could be a 2, a 3, a 4, or a 5. So if I put 4 choices there, why is this a problem for my second number?
If you have 3, 4, 5, or sorry.
Like there's going to be a problem with this. Why can't I just say, okay, there's 4 numbers left, why can't I just put 4 there? What's the issue?
Because if the first number is 2.
If the first number was a 2, then I don't have 4 choices, right? Because then I can't pick one, it's not going to work. See how that's an issue? If I did decide to do all 4, then I have an issue that I don't know what I can put for my second number because my second number depends on what I chose for my first number. Okay? So what we do is we break it up in cases, and I like, as a sort of a systematic way of doing my cases, I like to start with, and the numbers that would guarantee that it's bigger. The 2 is the problem, I'm going to leave the problem for later. This is like how we deal with life issues. We've got a bunch of things to do. One of them's a problem. I'm going to do the other things first and leave the problem to the very end. Not very many of us like to be like, oh, I think I'll just work on the hardest and the problem thing first. So I'm going to leave that. I'm going to say, here's my 3-digit number. I'm going to start with a 3, a 4, or a 5. 3 choices. And then there would be no restrictions because I would be counting numbers in the 300s, numbers in the 400s, and numbers in the 500s, they're guaranteed to be greater than 232. So I've used up one number. I don't know which one, 3, 4, 5, doesn't matter. How many choices are left? 4. How many choices are left for the last digit? 3. Giving me 36 numbers in the 300s, 400s, and 500s. Not for B. In A, it said it had to be even. In B, it said just greater than 232. So case 2, now we deal with the problem. Start with a 2. And then there could be problems with the second number. So what would guarantee that it works? If I started with a 2, the 3 causes a problem the next time, right? So I'm going to start with a 2 and then guarantee that it's bigger by going 4 and 5 next. So this is a 2, one choice. This is now a 4 or a 5, giving me 2 choices. And can you see that now I'm counting numbers in the 240s and 250s? They're guaranteed to be bigger. There's no restriction on my last number. How many numbers do you have left? How many choices do you have left for this last space? You've used up 2 numbers, right? Even though there's 4 and 5 are here, you didn't use them both. You chose one of them. So 2 numbers are gone. There are 3 choices left, giving you 6. What haven't you counted? Case 3. You haven't counted numbers in the 230s. So this is a 2, and this is a 3. One choice and one choice. How many options do you have for your last digit? There's a restriction on it, right? Because it has to be bigger than 232. Can you see that only the 4 and the 5 are possibilities? Why not the 3? Because we already used it up. So there's only 2 choices there. Add them up. And we get 44 ways in total.